coming. I'm not sure, more people might kind of come in and get going here. I want to introduce Kyle. This is Kyle Kinne. He graduated last year from UCR here in E major, actually manufacturing engineering.
I graduated with mechanical engineering. Right now I'm a manufacturing engineer at Facebook. So while I was here, I was president for 3 years, president before 10. I focused a lot on manufacturing and process optimization when I was here. I did do a lot of design for the IC car, which I think outdates all of you at this point, possibly. Process optimization and manufacturing is kind of my specialty. So my presentation is kind of short. There's nothing like super groundbreaking here. So I'm really hoping that we can get, like, if you have any questions, if you don't agree with something I said, definitely like raise your hand. We'll talk about it. And while this is not a huge presentation, I think implementing some of the stuff I talk about is going to be one of the pillars of success for you guys when you guys start to design and manufacture the next car. And then at the end, I'd like to open it up to kind of some discussion on where you think some of the stuff I talk about is applied. So we'll get into it. So I'm going to mainly be talking about how to optimize the prototyping process. And prototyping is weird, especially to try to get some efficiency out of it, because it's a very high mix, low volume thing. So that means you're doing multiple unique parts, and then you're doing like 1, 2, maybe 4. If you're really lucky, you get like 16 or something. But like, we're not talking about high volume. So optimizing for something like this still needs to be flexible enough that you can make all these unique parts, design all these unique parts, but still do it in an efficient manner. Obviously this car is on a super tight time frame. I'm sure you guys all feel that with the competition coming up and all your reports being due. So the main point of a prototype is to prove a concept, and especially where this team is at, you guys fall into like the prototyping realm, right? You guys don't have like proven cars. There's a lot of uncharted territory for you guys. So you guys are definitely prototyping. And the other thing is efficiency is measured differently for prototyping, whereas like in production, you're talking about like part to part. You know, it takes me 13 seconds to make this part. That doesn't really matter in prototyping, because you're usually making one. So, you know, 1 minute, 2 minutes, these things add up in production, but you really don't care in prototyping. So efficiency for prototyping is measured from when you identify a problem to the final solution. So as soon as you realize, like, I need some way to hold the wheel on the car and still let it spin, to when you have like a finished, like, you know, upright hub assembly, that's the time you need to measure. Not so much like I put a block of material in the machine, I get it out in assembly. That time is not really relevant to you guys or prototyping. So what this presentation really is about is standardization. If I put that in the title, no one will show up because it's boring. So I'm going to go over what is standardization, why would you standardize a process or a part or anything. What are some different things we can standardize? And how do you go about standardizing something? So we're going to do a little Q&A to see what you guys have in your head. So who wants to tell me what they think standardization is to them? Paul?
So basically having everyone come together, or in a group of people, whether it be your organization or an international organization, like I say, you all agree on one way things are done, one process, one specification, etc.
Okay, yeah. Anyone else?
Being like consistent with units across like the entire car. Everybody uses metric or inches, but don't mix the two.
Sure, yeah, it's a very specific example. They add some standardization. So yeah, standardization is everywhere. All those rules you see with like, you got to use this grade bolt, that's standardization. You know, or the seatbelt or the helmet, those are all standards that you guys are already forced to use. So, anyone want to talk about why they think standardization is a good idea? Different people? Come on, use your head.
Reduces cost.
Okay, yeah. How does it reduce cost?
You reduce the number of operations required in machine sampling, for example.
Okay. Manufacturing. Yep. That's a good one.
Quality can be fun.
Yep. Okay, yeah, so I'm sure everyone's heard of like lean processes or lean manufacturing. And to implement something like a lean manufacturing method on a prototyping process is very hard because as a prototyper you have to have such a breadth of ability to make so many different parts. So the only way you can apply some of those lean manufacturing or lean process methods and reduced waste and inventory is to standardize, right? So you can reduce the number of tools. If you standardize bolts, you can reduce the number of inventory of bolts you guys use, as well as tools. Like, what's the most important wrench for working on any of the cars? 3/16 Allen, right? You can take apart like half the race cars with a 3/16 Allen wrench. But it's not on accident that happened. So when I was here, I pushed standardization on people, not in so much of a formal way as I think you guys should start standardizing processes. But when we were here, you know, we tried to do it, and this is something that I tried to start doing when I was here. It's just, it takes, you know, a lot of upfront time and some money to standardize something that at the time we didn't have. So how can we standardize? So yeah, we'll get into that. What can we standardize as well? Those are very specific questions that I have slides on, and we'll get into those. So basically, this is what my definition of standardization is. So standardization is the act of making a design or process conform to a predetermined set of limitations. So standardizing something does limit it, but you don't necessarily, like, don't look at the word limit as such like a bad thing, right? If you standardize, like there are standardizations for tolerances, right? So that's not, those are limitations on the size. But sometimes it can limit creativity in design, but I also am going to argue that's not necessarily a bad thing either. So yeah, why standardize? So reliability is a big one, especially in processes. So standardization removes variables from the system. So if you, for instance, at work, I do a lot of manufacturing on CNC mills. We have a process that is standardized to where I don't set up the machine, I don't build any tools, I don't find any work like offsets. I just put material on a vise and press go on my program. And it's so standardized and flushed out that we run unique parts that have never been proven overnight. So we press go and we go home. So it's possible. So I mean, if for those of you who have done any milling before, or set up CNC mills, which I know is not all of you, but some of you, if you can imagine just putting a block of material on the machine, pressing the cycle start button, coming in the next morning and having done parts, that's what standardization can get you to. And obviously there's a lot of work that goes into that, but yeah, so reliability is a big one.
So I guess one thing I'm curious about, like, not being super familiar with CNC stuff, are the type of things that you would standardize would be things like rotor speed of the drill head, or like
Yeah, so I mean,
moving across the surface or something like that?
So we standardize. We have most of our tools are standardized. So we have, like, there's different tools, different sizes, different drills, different cutting bits, different taps. We have a standardized list that are in the machine, like measured and everything. And we do our best to use those. And those get 90% of the, like roughly 90% of the work we need done. And then there's always going to be some weird, like, special geometry that we have to build special tools for. But yeah, so we standardize tools. We also have a system that basically all of our work holding is in CAD and repeatable. So we know just like certain points on the machine. So we can drop a vise and a piece of material in, and all that's accounted for in our software. So it's pretty cool. So does that answer your question?
Kind of. I'll talk to you about it.
Okay. So I'm going to argue that engineers do better with more constraints. And this is because this is how you guys are taught, right? You guys go to class and you're looking for one variable. You're given everything else usually. So the more constraints put on an engineer, the more it limits the amount of possible solutions. So the faster they'll come up with the solution that works, right? So let's say you're designing a heat sink. You can design it a lot faster if you know how much heat you need to dissipate, rather than just knowing how much power is going into the system and figuring out how much heat needs to dissipate, right? So the more information you have into a design, the easier it takes shape. And for you guys, right, you guys need to pump designs out very quickly. So you guys can start manufacturing them, testing them, especially testing them. Obviously, if you standardize, you less inventory. You're not buying like weird tools or specialty tools for everything under the sun, because one person wants to use M3 bolts, the other person wants to use 440, and whatever. If you put some standardization into it, then you can just take half the car apart with a 3/16 Allen wrench. And the same goes for bearings and end mills, drills, taps. So in the long run, you save money because you're not buying all these specialty tools or really long end mills or drills. So I'm sure those of you who remember me, we were always waiting for tools. we're always trying to make something weird. Because engineers are psychopaths. And unpredictable. And again, you can apply lean process methods to a prototype environment, which is really what we're trying to get at. So what can we standardize? The answer is everything. Should you standardize everything? Probably not. So like the big one is some design features. Holes for, so if you have a standard fastener list, you're going to have standard clearance size holes, which means you're going to have standard drills, right? So it all kind of works together. Corner radii and pockets. I'm sure some of you, used to ask me, I used to give you a formula. That was my standardization for corner radius and pockets. And that's based off the tools I wanted to use is what I made that formula of. Part sizes. So I'm sure you guys are all familiar with, raw material comes in certain sizes, right? You get an inch, you get an inch and a quarter. So if you take that into account when designing something, you can save material or make it fit something you already have or that you stock. And when you cut threads, if you're going to do standard bolts, 1/4-20, that means that whoever's making it only has to have tap or however you're threading it for 1/4-20. They don't need to stock, every single thread size that has ever been existed. You can standardize manufacturing processes. So as we talked about, you can standardize the tools in a CNC machine. You can standardize manufacturing processes. So maybe you get a lot of our parts kind of look the same. Semi-prismatic, some holes, maybe some bearing bores. So the way you go about making those, you can standardize, right? You face it, then you drill the holes, and you mill the features, or whatever. And then tolerances for pins, press fits, clearance holes, those are all standardized as well. And then obviously bot parts. So this is the big one I think for you guys to start on, would be like standardizing fasteners, standardizing bearings. On the electrical side, standardize as much as you can. I know I'm not as familiar with this, but fuses, connectors, wires. Maybe you don't need a certain grade of fuse for a certain area of the car, but you already have some somewhere else, so it makes more sense just to use that everywhere than to have like a hodgepodge of different fuses that you have to stop. There's something, fuse blows, now you have to go find that specific one rather than just having the fuse. Just things like that, and then testing procedures. So if you're going to test how well something cools a system, you should test that in a standard way. So when you test another cooling system, your results, it makes sense. You can see correlations between the two. So you don't want to just, so in your testing, you don't want to have each subsystem or part be tested differently, because then your results are going to have some sort of variation. You're not going to be able to get, results that you compare to each other. Yep.
It seems like for different parts, you have different procedures, different ways to test them. How would you go about standardizing two completely different tests?
Yeah, so I mean, like the big one, like each part is going to be tested somewhat differently, right? But if you're going to put, like, you guys haven't done as much testing, right? But if you're going to put something on like a vibration table, you want it mounted roughly in the same way. You want, the temperature to be the same. If it, like, you want to make as many of the variables the same as possible. So and it's not as simple as just like, yeah, we're going to test them all the same. But like you want to try to use the same machinery, just known values, so there's not error brought in from that. You get what I mean? So if you were going to test like a belt crank to see where it's going to fail, you would like do a little jig with like maybe a hydraulic or a pneumatic cylinder applying the force. And if you're going to test like a shock mount frame, you should rig up something that's similar because they are experiencing similar load like configuration, right? Like you have a force going into like a bolt that goes into the bracket. So you want to do those the same, right? You get what I'm saying? So that's more standardizing testing. And then like outside the scope of this class, or in this project, like if you do hardness testing, like there's standardization for like the needle you use, and like, so there's already standards out there for certain tests that you also should abide by as well. So now we ask, how do we standardize something? So a perfect implementation of standardization is not even noticed by the designer. So this is completely unrealistic because everyone designs in their own unique way with their own unique features. And if you let an engineer just go, he'll bring you something crazy, right? Like, so there's obviously going to be limitations, but what this is kind of says is you want to use some sort of data to determine your standardization, right? So you don't want to just say like, oh yeah, we're going to use 5/16 bolts for everything out of nowhere. Because if you look at the previous cars we've built, like a lot of people were using /20, right? So that's data you can look at. So you can go look at parts we've made, parts we've designed, and use those to determine where most, like your 90% is going to be. So how you go about this is determine your limitations. So these could be monetary limitation. It could be a practical limitation, like I have 30 tool spots in my CNC mill, or the rules limit me in some way. And define where I'm going to go an example of standardizing a CNC mill. This is what I'm familiar with. After this, I'd like to open it up to talk, just kind of brainstorm how you guys think standardization can be implemented. So this is just an example I'm going to run through. This is not like a real example. It's kind of close to what we have at work, but not like, I can't share a lot of the data we have. So a lot of it's kind of just trends that I've noticed. So, limitation, 30 tool pockets, budget, I work for Facebook, not considered. So, previous data, 90% of our parts are aluminum. 90% of our parts range, they can fit in a 1-inch cube to an 8-inch cube. 90% of the threads in our parts are 632 to 3816. Some of them also include those threads, but an STI, which is for a helicoil insert. And none of the threads are more than 3 times the diameter of the thread deep. This is pretty standard, there's no benefit after 3 times diameter for a thread. So that's the way threads work for thread strength. And the parts are usually weird shapes, and no data can be pulled from there. So, first thing you need to consider is multifunctional tools versus single function tools. So an end mill is a really multifunctional tool. You can make a lot of different shapes with it. You can drill with them. You can 3D surface with them. It takes a while, but it's a very functional tool. So compare that to a drill or a reamer, which can make a single hole of a single size. But they can make it at higher precision or deeper, so there's benefits. But most of our tool list is going to be end mills because of their versatility, right? So I can make almost any size hole with an end mill, whereas with letter F drill, I get a 0.257 inch hole. That's it. Thread mills are also a versatile tool. So instead of, I'm sure most of you are familiar with the tap, which you drill a pilot hole and you thread this tap into a hole and it cuts the thread. And you spin it out, your part has a thread in it. Those are single function tool because a 1/4-20 tap can't tap any hole but a 1/4-20 hole. Whereas a thread mill works similar to an end mill, but can cut different diameter threads of different pitches based on the geometry. There's different types of thread mills. There's single pitch, which are the most versatile, and those pretty much cut each thread, one revolution at a time, all the way up the hole. So they're slower but more multifunctional. There's single pitch threads, which can cut, the pitch of a thread at any diameter. So this works well for STI tools, or STI holes and regular holes, because the STI hole is just different diameter but the same pitch. There's also end mill type thread mills, which can actually just helical into solid material and thread the hole, so you don't need to pre-drill anything. And there's also drill type thread mills, which can drill the hole and then go back in and thread it. So yeah, single function tools, we talked about drills. Reamers are just a very accurate hole making method, but again, very limited. Taps, single thread, single tap, and a chamfer tool, all it does is really chamfer or spot a hole. So basically, you want to look at your multifunctional tools or processes and populate your system with those because they're more versatile, even though they're less efficient, but you don't care as much because you're not making thousands and thousands of the same part or doing high volume work. So this is an example of like a standard CNC mill tool list, right? We have 2-inch root mill, 1-inch root mill. These are like your big roughing tools. We got a selection of end mills. Yeah, I'm giving you this. Selection of end mills, selection of bull mills, some selection of ball mills. One chamfer mill because you don't want to waste time deburring parts. Letter W drill, which is, who knows? Letter W drill is clearance for 3/8 hole. Letter F drill. Okay, number 9. That's 1024. So, some clearance drills for some common sizes that are used, and then some thread mills. And these are, I would go with the multifunctional one, like the end mill type or the drill type. And even though they say like there'll be like a 3/16 thread mill. You could do any hole that has a 16 pitch thread with them. So yeah, and you notice that our tool, maximum tools was 30, but I've only standardized 24 of these tools. So the other 6 tools would be for building any special geometry that our standardization doesn't cover, right? And you're never going to be able to really standardize to a point unless, yeah, you guys are never going to be able to standardize to a point in which you can get every single part out of the standard tool list of 30 tools without like severely limiting like what you guys can actually do. So from my experience with this tool list, I could have, machined 95% of the parts I made for SAE while I was here. So it's pretty good. But again, if you have these tools built and measured, if you have your offset and CNC machine measured already, these aren't variables that you're worrying about, oh, did I mess that up? Did I measure that wrong? And this will allow you to move faster and not spend time building tools, measuring tools, finding work offsets in your machine. This is just a specific example. This is the last slide. So I'd like to open it up to some thoughts from you guys. Like, what do you guys think is a good idea to start standardizing? How to go about that?
Where do you set your machine origin?
Okay, so we have Lang. So we have Lang 0-point clamping systems, which pretty much use like these pulled stud type things that are at the bottom of all of our vices. So they automatically locate the plates we have on our table to like 210s or something. So our zeros, on like our big CNC we have 4 different like zeros. And just depending on what plate you're working on, that's the zero to use. But it's just in the center of the plate that you put the vise on. And we have all of our vices in CAD, so everything is compensated. We can start programming the part.
How would we standardize our CAD drawings?
So standardizing CAD drawings. Like what? Well, I mean, what are you using your CAD drawings for?
Like Dave wants it in a particular way, and other people want it a particular way. Is this going to take more time changing the drawings into what they want?
Yeah. So I mean, like for standardizing CAD drawings, like the benefit you would get out of that is that anyone who looked at your drawing would know exactly what it says, where everything's at. It can interpret it well, but like if you're using your CAD, like there's already. So I mean, it depends who's looking at this drawing and what are they doing with it. Okay, Lane, what are you doing with your drawings?
Looking at it and making it apart.
Okay.
Make sure that I can understand it and like I know where to set offsets and stuff. And there's not just like random dimensions everywhere. They're very like organized drawing.
So as far as that would go, right? There's a standard for making drawings already. GD&T 2009 is I think industry standard right now. And for dimensioning, basically, you put the dimensions you care about, right? You need to dimension it in a way that, like, if a bolt circle needs to be within a certain position around, like, a bearing board, you dimension it in that way so the person making it knows. If you do everything off of one corner, then but you really don't care about that corner, right? It's just floating in space, there's nothing mounted to it, then why dimension to that corner? You know what I'm saying? So this just goes to GAT, like establish your datums where they matter, on faces that matter, and then dimension things from the datums that you need to dimension them from.
It depends on the machine you're using too. So if you're dimensioning something to be made on a lathe, you would dimension it completely differently in one way than you would if you were down on a manual mill, than you would if you were down on a plastic mill, and so on. So we just have to keep, that's why Aaron's job is kind of to check that stuff and make sure it's drawn the right way. But even across all of the machines, PGT standardizes where all of those machines are from and how they should be formed.
And that's something this school, industry, mechanical engineering does a horrible job at. It's teaching you guys like drawing stuff. So, anyone else's thoughts?
How do you go about standardizing features like wall thicknesses or corner radii if there's no numerical data available or historical, like if it's something that you can't find information on?
So yeah, corner radii is usually going to be defined by the tool, right? So if we look at tool 3, which is half-inch flat end mill, and it can cut 4 times diameter. So that means if you have a pocket that is 2 inches deep, the minimum corner radius I could put on that is half the tool, right? Because that's just how milling works. So standardization of that stuff will come from some sort of standardization of the tool, but the tool comes from parts. So it's very much an ecosystem that you guys have to kind of work through together. And it's hard because, you know, a lot of the decisions on past cars were intuition and not like actual numbers, right? Like the quarter 20 volt was the standard before I got here. And, you know, we just kept running with it because it kept working. So as far as wall thickness goes, that really depends on the part. To an extent, like milling a really thin wall sucks, so you guys would probably put a limitation like anything under a 16th wall thickness is just not acceptable. So again, it's not simple to do this because everyone kind of needs to work together to determine these values, right? So if you guys say that, like, you know, I can put a half-inch radius to 2 inches deep, and that's the limit, what happens when you get parts 3 inches tall, right? So you guys got to really go through these decisions, like look, see what that means for, like, if I standardize this tool, what does that mean? I can make a design, then look at designs, see, you know, how badly would that affect something. You know, and if it says, you know, 90% of the parts are not affected, then you're probably good.
Would you say there's a specific point at which like standardization starts to cause problems with innovative solutions?
Yeah, I mean, absolutely. It's always a trade-off. But you'd be surprised how crazy of parts can be made with this tool list. Those wheel centers, down to like the bearing shields in the motor, like the outside, the big housings took a special tool, but it's Yeah, there's a point at which the standardization will start to limit you too much. And then there's a point at which if you allow too much in, then your standardization doesn't work. So it's really finding that band at which you're not limiting design and innovation, but you're also still getting the benefits of standardization.
And that would tie into what you were saying earlier about how you operate better with constraints. It's just a matter of not over-constraining things.
Yeah, I mean, so engineers work better in constrained situations to an extent. If I constrain the system so much that you can't come up with a solution, then obviously you're not working very, very well. But if I say, like, if you're sitting there, you know, doing simulation on whether you should use an M6 bolt or a quarter 20 bolt, that's generally a waste of time, right? But if I don't give you a constraint, and you don't have any preference, and that's the road you go down. So standardizing just helps keep things moving and stopping, you know, a lot of that practical design from taking too much time.
While you were at UCR, did you guys develop any type of list of like standards you guys kind of just came up with and like, yeah, just throw it on a list?
No.
No?
I mean, they're mainly, it's like, as some of you know, like I was the main manufacturing force for most of the time I was here. So I kind of just operated like, yes, I'll make that part, no, I won't make that part. That was kind of my implementation of standardization.
How did you actually, you mentioned earlier that you had a formula set up for how it's ridiculous in the market. How did you actually develop that?
Like the formula for the corner radius?
Stuff like that, yeah.
I mean, it was pretty much like what I just went through with the end mill, except I turned that into a formula because all you engineers love formulas, right? Like, if I give you a formula for a number, then all of a sudden you guys feel like that number means a lot. And you don't fight with me as much on, you know, putting that corner radius there. And it all came from the tool. So pretty much, you know, my standard was like 4 times the diameter of the tool. I multiplied the radius by, you know, 1.5 for when you're milling into like the corner, your forces go up. So, I mean, there was a reason behind it. Yeah, it wasn't anything super special.
Is this a good example of something that you recommend pitching to Matt?
Yeah, so
At the end of the day, it is his machine, right?
yeah, that's the other issue. So I mean, there's ways to do it without affecting him. We all know he really doesn't use the machine that much. But when he does, you could just have the numbers in an Excel sheet, right? For all your tool offsets or work offsets, because those aren't going to change if you set this up correctly. Then you could take everything out of the machine if you need to use it, clear it, and then when he was done, you know, just type all the numbers back in. And it's not ideal, and it does, you know, add a step in which someone could, you know, fat finger a number, drive a drill into the table, but it's better than nothing.
I did already pitch it to him, and he loved it because it was Kyle's.
Kyle's a good person to answer that question.
So this is kind of a vague question, but other than experience, how did you gain your intuition for what just feels right in terms of manufacturability? Like when you make those decisions to say, like someone comes with a design to you and then you say, no, that's not going to work, or yes, that's going to work. Like, is there a way that you could like kind of more methodical gain that experience without putting, I mean, obviously you've been doing this for a very, very long time.
So, I mean, I feel like at some point it takes someone with experience, but once you do create the standardization, then it doesn't, right? Because then you have some concrete to go on. And you could, you know, pick a book up and like write a simulation for what it, like the cutting forces would do, but it's just not worth the time. So I would say, you know, intuition and previous experience to build the standardization is how, especially for manufacturing, is how it would have to go. That's kind of how manufacturing is, unfortunately. But again, once that is set up, then it doesn't matter if you've never seen an unknown in life. That standardization will tell you how to design something that's manufactured.
What would be like the optimum time to implement standardization?
Now. Right? I mean, it's really, you want to do it before you start designing something. Because, you know, manufacturing side has to make whatever you guys design. So if you try to standardize some manufacturing after you let your engineers go wild, you're never going to be able to do it because there's going to be too much variance in hole sizes, threads, corner radii, shapes, parts, materials of parts. Yeah, so I mean, you guys for you know, different things. Like a lot of these tools probably wouldn't work on any steel parts. And they're not a lot in the car, but there are some, like gears, brackets on the frame and stuff like that. But those fall within that extra percent. So it's not like this hard like limitation to where, you know, I won't make anything outside of this tool list. It's if we can try to use this tool list as best as we can pump parts out faster. We can test them. We can figure out we need to shim the uprights. Shim the uprights, test them, figure out the next problem, and, you know, move on. So the faster you can turn around parts, the better. Anyone else? Okay, well, you have a question?
Yeah, kind of, out of curiosity, how many iterations of parts like, would you consider like an upper limit after what you just say, okay, next to this, like, we're not going to get it better to go with it?
For this team, like, I mean, you guys don't have time to make more than like, I would say like 2 iterations before you have to just go with it. Obviously, the more you standardize, the faster you're going to be able to do things, so that number might increase. I know you guys have been talking about getting sponsors to make some parts. That could take some workload off you, those numbers might increase. But I would say there's like 3 types of ways to go about design. There's like pure intuition, then to testing, and then rework, testing, redesign, testing, you know. That way's probably the slowest. Well, maybe. That one's slower than, you know, design a part, run it through some simulation, make it, test it, then go from there. And then the other one is to get so bogged down in design and do so much simulation that there is no, like your part is perfect coming out, but that takes so much time as well. So there's this like balance. So So yeah, I would say like you obviously want to try to do as many as you can, but more than 2 on this team and under these time constraints would probably be too much.
Usually the only time we make more than one version of a part is if we fucked up the first one. Usually we try to take most of our hair out of the design process and the iterations on the design. That way we only have to make one version of the part. We try not to manufacture a part more than once because it's more setup and more cost and material and it just takes more time than we have here, more money than we have here. So usually we try to get everything worked out before we can really manufacture. We don't usually iterate on manufacturing. Usually it's like that.
So yeah, for this, like this club and these cars, your goal is a working prototype at the end of the year. The next year should be the iteration, right? So you don't have time to go and make multiple cars and test them, try. You might have, you know, some room for testing and optimization on some like specific things, but definitely not on a whole car basis. So the more cars you guys make, think of that as each like testing and design cycle. So yeah, usually you guys make one set of like a system, and then test that at competition. That's kind of how it goes. And that's why teams who've been doing this for a long time have really good working cars, because they use each year as a new design cycle from the previous tests. Anyone else? Okay, thanks for coming. Anyone who wants to come, I'm going to go get some dinner and some beer at Getaway. You're welcome to come hang out, talk to me about whatever you want. But yeah.